Well, good morning, everybody. Thank you for coming to my talk. I know it's still early for some people, it's even early for me. There's not so many people. Maybe malware is more interesting than IPv6. Well, which we're nearly at my first topic of this talk. First, my name is Mark Heuser. You might know me from SUSE Linux because I wrote all the security stuff in SUSE Linux, like the SUSE firewall, hardening, security check scripts, and stuff like that. More probably you might know me as Van Hauser, one of my pseudonyms where I program Hydra and AMAP and THC-scan and other stuff like that. Has anybody of you saw the slides or even heard my talk 5 years ago on IPv6 security? Anybody? No, you're still too young then, right? 5 years ago in IPv6, huh? Okay, what we see here, what we see everywhere is, when we talk about IPv6 is something, I think people have in mind something like Star Wars. Like, oh, in some distant future, maybe we will have IPv6, hopefully not, maybe we can dodge the bullet. Maybe it will pass. If we don't react to it, we ignore it, maybe it will just wander away and we can do stuff which really matters. That's my image I have when people talk about IPv6. So hopefully it will not affect us because we already have enough stuff to do. Well, in reality, there's nothing to dodge because it's already there. First, when we talk about the operating systems and routers and firewalls and stuff, they all come IPv6 enabled since 5, 6, 7 years already. So the IPv6 stuff is already there. Now the question is, when will IPv6 really come, being introduced so it's there? Well, next year. This is because a big telco provider like T-Mobile, or even I talked to one guy who works here at a mobile company. They said they don't have IP addresses anymore. And the more mobile users come with their mobile phones who wants to be always on and check their emails, they don't have the IP addresses for that. So what do they need? IPv6, because they don't get new IPv4 addresses. Additionally, I know from Deutsche Telekom that they are currently starting to deploy IPv6 connectivity for business customers. So you don't get IPv4 internet connections anymore when you go to Deutsche Telekom, but you will start to get IPv6 connections. And same for DSL. 90 to 95% of all the DSL internet connections in Germany are by Deutsche Telekom. All the others, 1&1, Freenet, and so on, are just resellers of that. And they also have to introduce IPv6 next year. That's why they are heavy scrambling to get it running. And now we see some, well, human nature. Oh, it's still so far away, it's still so far away. Enough time to do stuff. And then one day before, oh fuck, now we have to do something. And then you get results like we see in this talk. So let's start with the basics, because I'm pretty sure not everybody is used to IPv6. And I should start by saying this is a technical talk. And I think, well, it's even the first technical talk for it, because the talks after this one will also be all technical, finally. So IPv4, that's what everybody of us has currently. It's 4 octets. We have 4 billion possible IP addresses, and on the bottom is how an IP address might look like as an example. I hope everybody knows that. Now, IPv6 address is 16 bytes long, so 16 octets. I don't know how to pronounce this possible numbers of IP addresses. Let's say it could be enough for a while. And how a typical IPv6 address looks like is like that. Looks still pretty short, and that has reasons, even if it's 16 bytes. If this is our example address, the 16 bytes are grouped by 2 bytes, which are presented in hexadecimal. They are separated by a colon instead of a point or dot in IPv4. Leading zeros are omitted, so it would be 0004. And the longest chain of zeros are replaced with just 2 colons. Because of that, the IPv6 address can look very short and even shorter than IPv4 address. But in reality, it's very long. A subnet, a typical subnet, and this is a standard, and this will be everywhere. So this is not just hypothetical, or let's say only a few will really do that. everybody will use 60/64 subnets. A single subnet where you just might plug in 1 or 2 PCs, in other words, has the address space of 4 billion times the whole internet. So every subnet is large enough for everything we have already. There are no broadcast addresses anymore. So nothing like, okay, I address the remote broadcast and do some Smurf attacks. There are multicast addresses, but you can only access those multicast addresses from your local network. So if you want to access multicast addresses from a different network, it doesn't work. So this has some impact, especially when it comes to remote scanning. If you don't know what IP addresses the other end is using, well, how do you find that if the size of the subnet is 4 billion times the whole internet? Yeah. Big question. You can't just do a broadcast ping to make it easier to find something, well, because there is no broadcast ping. So you really have to test every IP address. Not groups, no broadcast, not the whole subnet. This doesn't work. So that's one of the issues when it comes, for example, to penetration testing IPv6 networks from remote. There are lots of features. One is auto-configuration. That's something which, in my opinion, is pretty cool. This is plug and play. You plug in a device, and you don't need DHCP because this is a DHCP replacement. Everything works out of the box. You get your local network address, you get your router, you get your DNS, everything. If there's a new router coming on the network, you don't have to configure anything. Everything is automatic. For the client, everything is auto-configuration. IPsec is mandatory in the protocol, so every device which has IPv6 also has IPsec, which is also a nice feature, if it ever is introduced on a larger scale. There is a mobility option, so this is not necessarily implemented everywhere, which means you can travel with your laptop, keep all your sessions, but travel on the train to, let's say, Brussels. In Brussels, you fly to New York, and there you go to a conference while all keeping your telnet sessions alive. So at least this is what the vision is. If it's really possible like that, well, but that's the vision. IPv6 is a lot about vision, how things could be, where it's not really sure if it will really work out like that, because there's not the deployment on the whole scale, so the experience is missing. And of course, enough addresses for everybody. I think I saw something like every square centimeters on planet Earth can have 10,000 IPv6 addresses. So it should really be enough. This is how an IPv6 header looks like. If you know how an IPv4 header looks like, you will see, wow, this looks easy, this looks simple. Where's all the stuff? Of course, yes, source and destination address is larger, but beside that, where's all the other stuff? And now the interesting question, what is the stuff which is missing? Yes. One thing which is missing is the IP ID, the identification field. First, there is no header length anymore. The reason? The header length is now fixed. IPv4, it's dynamic. So if you have options, the header can be larger. And this is bad for routers because they never know if they receive a packet what is part of the header and what is part of the data they are not interested in. So now it's fixed, it's 40 bytes. There's no identification field anymore, simply because they thought it's not needed. Now, after 25 years of IPv4 internet, we see it was an interesting idea in the beginning, but we saw it was not needed. So we can drop it from IPv6. There is no checksum anymore. In IPv4, there's a checksum on the IPv4 header. Now it's said, the internet is reliable enough that we don't need that, and if there's a checksum, it's done by the upper layer. So TCP, ICMP. ICMP version 6 has mandatory checksum. So it's only UDP where checksum is optional. And the checksum includes source and destination and the next header. There is no fragmentation in the header, and now it's interesting question, is there then fragmentation in IPv6? Does that exist, or was that also said to be unnecessary? We'll come to that. And there are no options, because then again the header would not be fixed. So every option is an extension header. Extension header is what is new in IPv6. Everything which is not absolutely basically necessary for routing a packet from A to B is optional. And optional means it's an extension header. It's a header of its own, which lies between IPv6 header and the TCP UDP data header. And there you have lots of stuff. You have the fragmentation, because not every packet must be fragmented, so it makes sense to make this optional and put it into an extension header. Source routing is coming back. Now we have source routing back here in IPv6. IPsec, destination options, hop by hop, there's lots of other stuff. So there's quite some headers. This is how a packet can look like if it has multiple extension headers. We have the IPv6 header. There it said the next header is a routing header, which is the source routing header. Yeah. Next header is the fragmentation header because the packet is fragmented. And then would be the UDP header plus the first part of the data. This is how an IPv6 packet can look like if there are more extension headers. So if we look at that, it looks much simpler. If you compare IPv4, IPv6, IPv4, this big header, so many options, what do you do? This is way simpler. So it should, of course, be more secure because we have all the experience with IPv4. IPv6 is just, we learned from our mistakes and made it better and larger and the features we might need in the future. So everything should be fine, right? Well, just in theory. As we can already start by seeing about, well, there are extension headers, we might assume that it's not so simple as it seems in the first place. For example, an extension header may be there only once, or is it legal to have two source routing headers or two fragmentation headers? In what order may the different extension headers may be? What options are there for extension headers? Because there are numerous options for every of these extension headers. And this is where it starts. This is just a start where things get complex. So IPv6 is, in reality, so much more complex than IPv4 that even all the designers of the IPv6 protocols and sub-protocols and stuff, and they're writing all their clever RFC and stuff, are overlooking vulnerabilities, even from all the lessons they learned in IPv4. So this is the reason why there are lots of vulnerabilities, and this is just the stuff which is in CVE, yeah, where there's a CVE code, a registration of a vulnerability. Well, we see 2002, there were 2 vulnerabilities, yeah, but you see, it's growing because more implementation, but it's also more awareness and more security testers. Yeah. This is what is currently in 2010, but the problem is if you register CVE, yeah, you get a number, but the number is just being published once you, as a researcher, say, now you can make it public, which means usually after a fix is there. So even in February, March, April of 2011, there will be new CVE, which has 2010 in there. Yeah? So this is why this is the expected gap, what is still in there. And it's not counting my own CVE entries because I still have to make them, which will be 3 or 4. Yeah? So this will even spike larger than that. So kids, in 2005, I did already a presentation on my IPv6 security research. Yeah. Now I will really shortly wrap up what I presented there, and then present new stuff. Of course, we are here because of new stuff. It all evolves around a toolkit I'm programming, because when I started to look into IPv6, I wanted to do some security testing and noticed there are no tools. I want to see how this works. I want to create that packet, and there were no tool available to do that. Even the most basic attacks, no tool. Even today, luckily Nmap can at least do connect scans on IPv6, and we have Metasploit, which has IPv6 support. But beyond that, still after 5 years, there is one more man-in-the-middle tool which implements the stuff I already implemented 5 years ago, so no new stuff, and that's it. Yeah? So everything in my research really evolves about that toolkit, which contains now, I think, 35 tools. So good luck, examine my toolkit, because you'd just be overwhelmed with all this stuff which is in there and not the best documentation, let's put it like that. So first, what we know in IPv4 as ARP spoofing, we also have in IPv6. There's not the ARP protocol anymore. It's done via ICMP6 types. Here it's called neighbor discovery spoofing. It works basically the same. Instead of an ARP request, you send a neighbor solicitation ICMP request to the network. The system which has that IP address you are asking for is responding with a neighbor advertisement back, which has the MAC address. Well, of course, anybody can answer to such a request, so we have a tool which is called Parasite6, which does exactly that. Listens on the network, and to every solicitation request which comes, it spoofs your own MAC or a random MAC or a fixed MAC which is not on the network as you like it. Then we have duplicated address detection DOS. This is something we also already have in IPv4, just that duplicate address detection is not done by many systems. In IPv6, it's mandatory. So what does that mean? Well, it's also done by neighbor solicitation tests. So the system wants to use a new IPv6 address, so it sends a message on the network, which is an ICMP, same type, neighbor solicitation request. Who has this IP address? Because I want to use it. Sends to the network, and if there's no reply from the network, the system knows, okay, nobody's using that IP address, I can use it. So there's not a duplicate on the network. Again, how to circumvent this check is create a tool which sends always, yes, I'm using that IP address, I'm using that IP address, I'm using that IP address. Yeah? So denying all new systems its IP address connectivity. Even works for existing systems, but for example, Sun Solaris, if it detects that its own IP address is in use, it shuts down its interface. So even for live systems which are already on the network, you can deny the network access. Even with Windows, it works. It's totally okay if you ask questions in between. I'm fine with that. Yes, Rafi?
If a machine
you can also, and I repeat the question.
If a machine does a neighbor solicitation, what IP address does it usually take? It's the one that the MAC address inside of the IPv6 header, right?
Yeah. Every machine comes with an IPv6 address automatically, but it's just a link local address.
Right. So every machine should have a unique address that it asks
but even DES has to be solicited because DES address could be already being used. This is why the source address is unspecified. Yeah? So there's no IP address in the request, which is, of course, where would the system send the answer, which is to everybody. So the answer which this tool is sending, or a system which already is using this address, is sending to everybody this address is in use.
But theoretically, if my MAC address it should be unique worldwide.
It should be unique,
the IP address should
especially
be
if there's somebody evil, or if you use, for example, privacy option. The privacy option generates randomly every day a new IPv6 address, and then has to check if this address is already in use, because the more systems, the higher chance that in 10 years there's one collision. You can do man in the middle with redirects. Redirects already work in IPv4. You also have them in IPv6. And the good thing about the redirect attacks on IPv4 and IPv6, they work by default. Because secure redirects are always enabled. If it's Windows, if it's Linux, doesn't matter. If the redirects are secure, secure means it comes from your default router and it contains a real packet the victim was sending, then the redirect is accepted by the system. And this is really easy to foil. Look up my slides from 5 years ago. It's all explained there, and there's a tool, Redirect6. IPv4, IPv6 doesn't matter. Implant the route, wonderful. IPv6 is just more secure in that regard that this attack only works locally on the local LAN. On IPv4, it works from the other end of the world, if you know what the address of the default router is. Then we have DHCP, or better, auto configuration, because this is what originally they wanted to remove. An extra service, DHCP, nah, we are cool people, we do everything out of the box on the network, it's auto configuration. Nobody wants DHCP anymore, which works with router advertisements. So you have a router, and the router advertises on the network, I'm here, I'm the responsible router for this network. This is the IP range from which you should use yourself, your IP address you want to have. If you want to use a DNS server, this is the IP address of the DNS server. So this is done all by the router. But what happens if if you set up your own router. There's a feature which is about router priority, and by default, all routers set their priority to medium. If I start my own fake routing advertisement daemon on the network and says my priority is high, I will be the default router. Yeah. So this is 50% of my talk from 5 years ago, but let me continue on the router advertisement stuff because there's so much you can do exactly just with that stuff. Yeah, kick the default router. So there is a default router, you don't want that default router to exist anymore for the target. Easy. You send your own router advertisement, so you will be the router afterwards. So this is already so that you're already in the routing table, but this is still the default router for whatever reason. You spoof a router advertisement from the default router, but with a 0 lifetime, because a router advertisement has a lifetime. So how long is this router active? And if no new router advertisement comes, then consider this router as dead. So you spoof a router advertisement and says 0 lifetime, which means, oh, I'm dead. So just to be sure you're really the default router afterwards, you send again your own router advertisement. This router is dead as long as it doesn't send its own router advertisement again, and you are default router. And the default router doesn't exist anymore for our target. We're coming back to this point because you could say, okay, but if you spoof the router advertisement, the default router will see that and can react on that. I show you later for a different kind of attack on a different protocol how I can do it that the router doesn't see that. Kill all routers which are on the network, and the target systems will think that all internet is local. This is in the protocol. Actually, I haven't tried it if it really works, but it's in the RFC and it has to be implemented, otherwise the system is not RFC compliant. That if there is no router on the network defined, everything is local assumed. Because then there might be a router who just picks up the traffic and then forwards to the right direction. So it's another, let's say, if something doesn't work because of router advertisement is somehow accepted by a system, everything can still work. Another thing which happens if you send out a router advertisement is that all the systems start being dual stack. They already are IPv4. They have the IPv6 capability. They're just waiting for a router advertisement to tell them, hey, IPv6 is okay here. And once the router advertisement is received, they are dual stack. They're IPv4 and IPv6 enabled and use both. What could probably go wrong here? You can port scan on IPv6. Yeah? So once you say, and now here's a router advertisement, the system configures its IPv6 address, you can scan that IPv6 address. By a duplicate address detection, you know what the new IP address is it's choosing, and then port scan that. And as IPv4 is a different IP spec than IPv6, you must have filter rules for IPv6. Otherwise, there are no filter rules, and you can port scan all ports without a firewalling in between or port filtering. It will prefer IPv6. So if it does DNS requests somewhere, an IPv4 and an IPv6 address is received, it must use the IPv6 address. So how about create a tunnel, so you really implement IPv6 connectivity and tunnel in all the IPv6 traffic through you and sniff everything, or announce a remote network address space like PayPal locally on the network with a remote router advertisement. So if a system wants to connect to PayPal, they think, oh, that network's local, cool, yeah, but it's your system. So there's lots of stuff you can do just with router advertisements. What you can also do is router advertisement flooding. And actually, that was something where I was thinking, I mean, of course, if a system configures its IP address based on the prefix a router is announcing, so this is a network here, and you can have multiple IP addresses. You can have 10, 15 IP addresses on IPv6, no problem at all. And it's normal that you have 3, 4, 5 IPv6 addresses. Right? This is how it's designed. The next step, what happens if I simulate 10,000 routers and they're all announcing different networks? So 10 different IP addresses are configured. What does happen? So for me, let's say in a hacker security researcher's mind, that's just the next step. Yeah? It's very easy to come up with that idea. So what could probably go wrong with vendors? Yeah? These are the affected operating systems, which when you start attacks, 100% CPU load, 100% RAM usage. So they're doing nothing anymore. Yeah? Cisco RZ, Cisco PIX, old Cisco iOS, Windows 2008, Windows 7, Windows Vista, old Linux, but really old. Yeah? Maybe more. That's just what I tested. Yeah? How can that be? You must be local on the network, because that's where router advertisement are received. So here, for example, at the conference, you can just do it, and everybody of you who is using Windows would not be able to do anything, yeah, until turning off, rebooting, and having the same problem again. So what do vendors do? Well, they fix. Cisco just fixed it for the iOS. This is the bug fix ID for the iOS. In ASA, this is coming soon. I was told next week in 2 weeks. This is the bug fix ID for that. And Microsoft, it's not a problem. We implemented it like it's in the standard. So if it's in the standard, it must be okay. If our systems are not accessible anymore, 100% CPU use, well, is that our problem? Yeah. Apple is not affected, by the way. So they got that thing right. Linux doesn't. Cisco fixed it, but Microsoft says it's not a problem? Unbelievable. Yeah. Some jerk said 5 years ago, because of this vast IP space in just a subnet, and because we don't have broadcast and stuff, it is not possible to do remote alive or ping scan on IPv6 networks. The jerk was me. Okay, I admit. By doing some more IPv6 research, I came up with some ideas. Some are very easy to come up with, but actually I needed some research on that, so statistic research. How can we identify remote systems in IPv6? First, we can not scan the whole range. Yeah? If it's 4 billion times the whole internet, it doesn't work. Yeah? It would take, even if you could send 100 million packets per second, it would take 10 years just for that one subnet where maybe just 1 or 2 systems are there. It's not feasible. There are no broadcasts, so we can't do that. What is obvious what we can do? We can use search engines, public databases, for example. Yeah? We can check the web page of a company to see what IPv6 they have. We can look in the DNS. So we can do DNS brute forcing. We can see what is the mail exchange, what is the name server, and see if they have IPv6 addresses there. And we can look for common addresses. And we're coming to that. And if you combine them all, maybe there's a chance we will identify some systems. So I was interested in how many systems are that if I combine these. So I looked into the search engine, dumped various IPv6 directories which needed some web app, not hacking, but let's say query manipulation. So I could generate 14,651 possible domains plus subdomains, and did a DNS brute forcing attack. So I took every domain I found in subdomain and brute forced 3,000 possible host names. So I used what are usual host names on IPv4. I added some. I took the one from Metasploit. I got some Word text files and put them also in there. So 3,000 is really lots. And I found 40,000 DNS entries. Well, the point is, if you're looking for VPN as a host name and you're just looking for VPN, what are your results? Your results are everything is VPN out on the internet. Of course, because you're just looking for a VPN. So this might not be the right approach to talk about what are common host names, because if you're just looking for web, yeah, we will just see www. But what we can do, we get from the DNS entries, these are about the host names, which we skipped at the moment, we find the IP addresses. But on the IPv6 addresses, now we can do statistics. Yeah, so I found 40,456 unique IPv6 addresses in 12,942 networks and 5,434 unique host addresses, which means unique host address is the host part. So if you have a C-class network, the most common host part address is .1. Well, as I said, /64 subnets mean you have 4 billion times the whole internet as possible host addresses, getting down to just 5,400 values being used, it's not a large key space, so to say. So this is the distribution of host addresses. You will see there is one common address which was used about 1,800 times, and this is host address 1. And so on and so on. So what you can create is a dictionary list for host addresses on IPv6. And if you look at this, you will see, okay, this is where things go slowly, but up to here, it's very effective. With just a few checks, you find a lot of systems. And this is here at about a range of 700, 800. So by just checking 700, 800 IPv6 host addresses on a subnet, you will find many, many systems, statistically.
Does that mean the first ones or randomly? Could you repeat the question?
If it's the first one, or if it's randomly, I'll come into that. Host address analysis. So when I got the 5,434 unique host addresses, I was looking at, okay, what are these host addresses? Where do they come from? Of course, some come from auto configuration, which is based on the MAC address. So the vendor ID is, well, let's say we come to, some are configured by hand, and others are configured by DHCP, because some people still use DHCP for management reasons. So auto configuration. Here, it's based on the MAC address or the privacy option, or it's a fixed random value, because there are different kinds on how you can implement that. Yeah? And it's on many operations you can choose which of the 3 types you want to have. If it's done by hand, it's either random or by a pattern. So pattern would be 1, 2, 3, 4, or 1001, 1002, 1003. And we have DHCP. DHCP, you define a pool, and all the implementation I reviewed, they give out the IP address sequential, which makes life easier. So if you got one system which is in the DHCP address space, you just look below and afterwards in that address space. Got it. So what I then implemented in my scanning tool, forgot. So here we see auto configuration, the MAC address, 24-bit key space, usually per vendor ID, which is possible to do. It's like a class A network scan. Privacy option, fixed random, no way. It's too random. By hand, well, if there's a pattern, of course, once you identify what the pattern is, piece of cake. If it's done random, well, bad. And of course, DHCP, again, is easy. So I implemented by hand the patterns I identified, and the DHCP, usually DHCP ranges. And if auto configuration is detected, the whole MAC address range. So because if you have one server by, let's say, HP or Dell, you might have more servers by HP and Dell. So just the last 3 bytes might be different. So that's when it's interesting to also search this key space. So if you configure something by hand, this is an example what our people are usually doing. Yeah? 1, 2, 3. The service port, so port 80 for web, for example, 53 for DNS server. Or 1, the service port, 2 and 3 and 4 if they have more of them. Or service port :1, 2, 3. Some use even the IPv4 address. Yeah? So 88:1:23:24. So if you know the IPv4 address, you know exactly what to scan for. And some funny stuff like boop babe, dead beef, foo, and so on and so on. These are the common DHCP ranges. So if you use DHCP S6, which comes with Linux, or iOS example configuration and stuff, this is what you will see. So I also added the first part each into my scanning tool. And this is what the distribution is like. Yeah? Auto configuration is this part, which is a larger pie. IPv4 addresses is not so often random. Good luck, is relatively rare. And the hard-to-guess addresses are also pretty large. But this large piece of the pie is what we can guess, which is roughly 66%. So my live scanning on the 12,000 were roughly 13,000 networks with brute forcing 2,000 possible host addresses, was 380,000 alive addresses. Some firewalls, so I scanned on ping, I did a SYN on port 80, UDP, a real a DNS UDP packet on port 53 and stuff. Yeah, and got more unique hosted networks. From the population, you can see that I'm still missing some of the possible addresses. So as this is still pretty steep and not a platform, there's still more I can identify. So I'm pretty sure until my next talk, because this is just scrambling because they asked me, oh, some speaker didn't get his visa, can you do a talk? So I'm not really done already with the research. I'm pretty sure I get to 70–75%. So the live scanning, I did the same on the reverse stuff. So I reversed all the DNS entries. I got the DNS entries of all the alive system and got 13,402 DNS entries. Yeah. The unique host names are interesting because now I could see, okay, these are the host names in DNS which are used. So I can feed this again into my DNS brute forcing for host names I didn't have in before, because now I see what is really used. And then you get new IPv6 addresses, you can check if there's new host addresses coming up, and so on and so on. So what you have here is an iterative approach. Until you have all the IPv6 host names which are usually used and all the host addresses of IPv6 usually used, and then you get a very good, very detailed picture of statistically how you have to perform your remote network scan to find as most systems as possible. So in conclusion, just by DNS brute forcing, you find 90% of the systems which are in the DNS on average. Pardon?
There are mistakes in this because you're basing all your numbers on this strategy of live IP hosts you know about.
Yeah, but I'm only checking for the reverse DNS, and that's where I base the stuff on. But it's not 100% because what put the in the DNS? Yeah. Oh, sorry, I'm not a researcher. I'm not academic. I don't care for academic stuff. I check for real world stuff, and it's good enough for me. We can talk. We have only.
Let's defer that.
With the live brute forcing, I see real systems, so I can see what is on the networks. Yeah? So I can see if what I found here is real life. Yeah? And it is real life. And as you can say, 66% on average can be found. And if you combine both, what is in the DNS and what you can get from the live system, and now it's get really very hard to say, but it's roughly 90 to 95% on average. Yeah, which means on some systems you will not find anything, and on others you will be 100%. Yeah, this is just the average on the average network. But we have lots more stuff. Now, attack on multicast listener discovery protocol, and how deny multicast traffic. Works like that. The router sends periodically a general query message to say who wants to listen to multicast. And everyone who wants to listen to a multicast address says, hey, I want to have the multicast DNS server traffic. And then the router talks to the other router. Whenever there is DNS multicast traffic, it sends to the network. What you can as a hacker do, you send a done message. The done message means I don't want to listen to the multicast DNS stuff anymore. You spoof that as A, and the router now thinks, okay, he doesn't want to listen anymore. There is security in the protocol that when that happens, the router sends again a message, which is, there's really nobody wants to listen on this anymore. And A would then say, I still want to listen. So this doesn't work. What we want to be is this query router. We want to become that. So we want to eliminate this one and be the query router. There is something in the protocol, because if there are multiple routers on the network, only one should be the query router. So the decision process, who is the query router, is who has the lower, mathematically, IPv6 link local address. So we first spoof the general query message, our own query message, as this address, which is the lowest possible address, and I've never seen it configured anywhere. Never, ever. So you will always be the query router afterwards. Then you spoof the done message for A. Well, what happens? It just only works for a very short period of time. Because if you, as a query router, do not send this general query message from time to time, the other router will become active again and say, oh, the query is gone, now I have to send the message. So still enough security in the protocol. So you must send a general MLD query message regularly, but in a way that only this router sees it and the target doesn't see it. So how can this work? And then a few nights ago, I had the idea. I just spoofed the query message with a special MAC address. There are multicast MAC addresses. Multicast MAC addresses specify who can receive that message. And if you send it with the multicast all router MAC address, only the routers will pick it up, even if the IP address is for all the systems. And this way, you spoof first the general query message to become the query master, spoof the done message for the system, and then send the query message from time to time, but with that special MAC that only the router accepts it, but the target message doesn't. And that way, you can completely disable the multicast routing into that part of the network. But there's more. In 1998, I found a vulnerability on Linux where you can see on the local network if a Linux host was sniffing. And guess what? On Wednesday night, I found the same vulnerability in IPv6 in Linux and Windows again. So re-implementing old vulnerabilities. You send a ping to the target with an unused multicast MAC address. If you just use any MAC address, it doesn't work. It must be a multicast address the system should not be listening to. But if it's TCP dump or any software like that is activated on the Windows or Linux machine, it replies with a ping, and you know the system is sniffing. Are there any side channels in IPv6? Another big, well, is it a big question? IPv6 is a side channel, especially if there's firewalls in between. The problem is that with all the extension headers, the firewall vendors can't really filter on the content in extension headers. I talked with Cisco about that problem. He said, because there's constantly design changes, because they can't anticipate what comes next in the standard, they can't filter on content in the extension headers. They know a few things which are evil, known evil, so that's what they filter, but everything passes through. So you can send whole Word files just in an extension header out through the firewall, and they can't prevent it. So if you ever see a talk, oh, side channel attacks in IPv6, it's just someone who got a boring talk because there are too many ways you can do this in IPv6. But in the end, don't be scared. With a good design, a good security infrastructure design on IPv6, you can eliminate a lot of the stuff. Not everything. For that, you would need to deploy IPsec totally and completely and stuff. But even with smaller stuff, you can do, for example, secure host configuration and eliminate some of the stuff. Yes, IPv6 is very complex. It's an intellectual challenge. The more you look into it, the more you understand how complex it is. And if you're a security searcher and you're tired of finding security vulnerabilities and stuff nobody cares about, like guestbook, PHP application, foobar, 0.1 beta, and you really want to find vulnerability stuff which is rather easy, because lots of stuff, but also which have meaning. So interesting vulnerabilities, IPv6 is the stuff where you should go to. So be an explorer. There is so many protocols. 100 people can study on that and still find different vulnerabilities and issues. So join me, join researching IPv6. It also makes the whole protocol more secure in the end. That's what hackers do. Criticize so things can be made better. So here's an example you can then see in the keys later in slides if you want to play with IPv6, how to get into your home. So encourage to see how easy the process is. And either you have a static tunnel or a heartbeat tunnel to your home. This is what you configure local homes. You have real IPv6 on your local network. List of everything which is new in my IPv6 attack toolkit, which is a lot of stuff. But it's not on public release still, because I'm still developing lots of this stuff. So it's not complete. But anybody who sends in patches and new tools gets full access. Also, I don't want lots of people to scan the internet now when I release the tool, when I'm still doing my research and see what are good addresses and stuff. But I will do soon a smaller update to the complete stuff. So this is where you can download the tool. After Christmas, I will enable a website here where you can find all information on how securely configure a PIX, how to secure a Windows host to make it, to protect it against IPv6 attacks and stuff, how to do a remote pen test and things. Yeah, and if you need if you have any IPv6 networks, you say, hey, I want an external consultant, help me design it, or pen test it, or please review this firewall if it's doing its job, well, ask me. Thank you. Do we still have time for questions?
We have time for questions.
Yay.
Okay.
3 minutes, yes.
Yeah, 3 minutes. First, a question of mine. So it's, your talk on IPv6 guessability of addresses will mean we will see something like uncrackable passwords, which are tested for IPv6 addresses too. So that probably what Ottmar was referring to, that statistically looking at that will lead lots of matches, but if people choose clever IPv6 addresses, they are less vulnerable. Is this
Of course,
the case? Yeah.
and that's also why I'm doing this presentation, to make aware, don't make it too easy.
Yeah.
If you have the possibility to make it random, do it random. Yeah, I mean, that's the point.
Okay. Any more questions, Ottmar? You?
One word before you start talking. I don't say ever this is 100% and mathematically whatsoever. Yeah. I'm not a mathematician guy. Actually, I'm more the practical guy.
Yeah. Okay. Something different. Regarding route announcements, advice from me. This does not have to be some evil guy. This might be just someone who's running Curator on his laptop, comes to your IPv4 network, enables his tunnels somewhere else, and then plays router on your own network. So this happens on the real world, even without malicious intent, that somebody plays route announcement on your network. So if you really run v6, try to block all the tunnels, because you will get a different route announcement in your network. So regarding the numbers from before, what's your overall count of live IPv6 hosts out there? Because all your numbers you get on, I found this many real individual live IPv6 addresses, makes, or numbers in terms of percentage, have to refer to some overall totality of live IPv6 addresses.
Mm-hmm. The point is, nobody can answer you this question, how many IPv6 really alive addresses there are. I can just say, I took as most networks I can, which I personally would assume that I found about 50% of the whole internet too. But it could be 80%, could be 20%.
So
and I concentrated on the end networks. So of course all the transport networks in between, the routing networks, I didn't scan these.
the routing is simple because you just have to do trace routes to see the route IP addresses.
Exactly, that's why I didn't care.
My guess is that what you found are mostly the servers or manually configured boxes, and all those mass deployed DSL, whatever, out there in Asia are using random addresses which you probably haven't found in your scans.
Mm-hmm.
So when you say with your tools and your brute forcing you get 80% of the hosts, then that's 80% of the hosts you found with all your other mechanisms.
Yes.
That was a bit unclear in your slides.
Yeah, totally true. But then again, who would, if in a remote pen test, what would you look for? In a remote pen test, I would be authorized to please check the security of that company, and I wouldn't care about DSL users, which is a different goal. But I could have said that more in the beginning, yes. You can only find stuff you are looking for. This is always the problem. Only if you look for money on the floor, it's more plausible that you find money on the floor. If you buy a new Mercedes, which is very brand new, you will notice, oh, many people more have that, and before you would not have noticed. So you usually find only what you're looking for, and this is the problem.
I'm a bit late into this presentation, so I don't know if you asked before, but who in the room here has v6 at home? In the office?
Which is
at work? Whatever?
more than I expected, actually.
So who has ever configured v6 on a router?
It could be way more, and will be more in a few years.